Alright. Hi guys. This is the first time I've done this, so I don't know how it's going to go. At any rate, what I want you guys to get out is the lab sheet that we worked on. Hopefully I can make this happen. It's the lab sheet, the stations lab for the abiotic chemical testing that we went over. And I just want to go over every one of the labs with you and tell you which things are the most important for you to have found, and then kind of go over the calculations in case you're having trouble with that, so that we can make sure everybody's on the same page. You will be able to use this document on day 2 of your test, so that's the other thing that's important to remember. Alright, so for station 1, basically that one went over temperature, and the most important thing about that temperature, the thing that we really want to worry about, is the distance, or the difference in temperature change between distances. So when we're monitoring a stretch, what you'd want to do is actually measure the top 200, so the most upstream 200 feet, and then the most downstream. Honestly, the other thing we look for would be another spot downstream. So we would take a temperature reading completely downstream, maybe somewhere near the confluence, J Street, something like that, to get a temperature difference. You do not want a difference more than 5 degrees between 2 points along any stretch of creek. So even from the headwater to the confluence with the next stream body, you don't want more than a 5-degree temperature change. As you guys know, too much heat is going to cause a release in dissolved oxygen, and so we definitely don't want to see a temperature going up above that 5 degrees. Plus or minus 1 degree is pretty good. That's hard to find in an urban setting, but that would be what we want to see. So the most important thing about temperature, when you look under summary and description of pollutant, you just want to make sure that that temperature isn't too high. As you guys, we've talked about this a million times, if the temperature is too high, or as the temperature's high, it's going to release oxygen, and we want the most oxygen possible. So according to Poplar Creek's fake data that you guys had to assess, there was no temperature change between the 2 points. Again, anything greater than 5-degree difference is going to be a problem for range acceptability, and if we were talking about a trout stream, we'd want to see less of a change, because those are critters that definitely need a high amount of oxygen, and so cold temperatures are the things that are going to produce that. So what could cause a temperature to increase? Well, the things that cause temperatures to increase are typically discharge, so point discharges from factories. So in this day of industrial age, and especially back into history, most factories were built near a body of water, and the whole purpose of having it built near a body of water was so that they could take water into the system. They would pipe it through the factory, and that's how they would cool the machinery. So the water would then absorb the heat, and then that water would then be released back into the waterway. And you guys know some of the characteristics of water, and one of that is holding capacity, heat capacity. So it would, basically we're releasing this warm water back into the streams, and that would increase the temperature artificially and immediately release all the oxygen. So that's one potential source of a heat. The other thing that could happen that could really increase, we don't worry too much about being cold. I don't know that there's anything so much as too cold. They're never going to freeze all the way. It's not going to freeze so solid it kills everything that's in the waterway. So we're not so worried about freezing. It's warm that we're worried about, the heat that we're worried about. So the other thing that you might take into account then is the canopy cover. If there's not a lot of canopy cover, then in those summer months that water's going to heat up and release a lot of oxygen, and that's a bad thing. We don't want that to happen. Alright, so station number 2 is pH, and you guys understand the pH scale. You learned it extensively in biology, and then also in chemistry and physical science if you took those. So basically pH is just a measure of either the presence or absence of hydrogen ions. And like most things, that are living, there's kind of a just right. The story of Goldilocks, right? There's a just right. And so the range that we have in this region is 6 to 8 for pH. We want to see a good, healthy pH range of a 6 to an 8. In this case, we've got 8. We've talked about this before. I know for sure in 3rd hour, maybe 8th hour, I might have missed you guys, but our region has dolomite, limestone underneath our ground, and so that is definitely a limestone that's going to release and cause release lime and cause our waterways around here to be a little bit higher pH. So you may actually find in this region pHs and waterways that are around a 9, and that would still be acceptable. Not acceptable for all life, but would be pretty normal for around here because of that dolomite limestone. Now, by the other token, you can have things like acid rain, which would greatly lower the pH. Any of the lower pHs are going to create tons of problems for amphibians and fish to reproduce. Their eggs have a very set range in terms of what pH is acceptable. So acid rain would be an issue, and by the other token, if we had some kind of a release of a base that would raise it above an 8, and especially above a 9, there would be significant problems. One of the other pollutants that we're having problems with around here that I'll just kind of mention is actually road salt. Road salt is causing, it works like a water softener, and in our ecosystems that we have here, like fens, you've got a calcium, we've got a calcium-rich dolomite kind of water system, and when you put road salt on there, that sodium will actually trade places with the calcium, and then we get a water softening effect essentially, and that does create lots of problems for our kind of specialized ecosystems like fens that are a little bit higher pH. Alright, station 3 is phosphate, and phosphate is it's a necessary, plants need some phosphate, some naturally occurring phosphate in order to grow, but our problem around here is that we have too much of it, and that would go along with nitrogen as well. It's being released in fertilizers in a significant amount, and when that happens, it causes plants to bloom. It causes algae to bloom, both of which have shorter lifespans. So these plants and algae die. They sink to the bottom of the waterway where they're digested by bacteria, and the bacteria needs a lot of oxygen in order to perform that decomposition, and so you have another situation of lowering the dissolved oxygen that's available just because those bacteria are working overtime trying to decompose the plant material that's dying. So Poplar Creek data range, we have here a phosphate of 0 milligrams per liter, which by the way is equates to parts per million, just so you guys know that. And that's pretty normal actually. If we were to have done the actual water testing and gotten a phosphate test done, it would have shown up as a 0. This time of year, you don't see a whole lot. Now, the end of November, after everybody's winterized their yards, and into December, then we'll start to see kind of significant phosphate levels with just our testing kits in the high school setting. If you had a more sensitive test, you could probably pick it up, but that's pretty standard right now. Orthophosphate, as you guys learned, is a little bit of a different situation, and we want to keep track of both of those. So in this case, we've got a 0.07 milligrams per liter. What I want you guys to know is that there is no state standard for phosphate, and there's no state that there's no federal standard for phosphate, there's no state level for phosphate. There should be. It is really, if we're going to learn about it more in this next unit that we're doing in terms of water, it's really a significant problem. Right now, a lot of states are trying to use the state average. They just don't want every region to go over the state average, which just, that's just completely silly to use the state average for that. What you should keep in mind is that most critters, of the critters that you guys met when you were doing the MBIs, they really can't stand more than a 0.2 parts per million. So anything above that is harmful for them. Now, we don't worry so much about phosphates with humans. We should, because there's secondary things that can happen, but there's not a lot that can necessarily happen to us from water consumption of accumulation of phosphates. So that's why they don't worry about it too much. Again, potential sources for that one is definitely going to be fertilizers. Nitrogen, on the other hand, we would definitely pick up nitrogen on in our chemical tests if we would have done that. And nitrates and nitrites, you've got the levels there of 0.2 parts per million and 0.5 parts per million. And again, there is no standard. They just use the average, and that's, you know, for obvious reasons, that's really a silly way to do it, but that is how they do it. And what you should know is that our critters that you guys met can only stand 0.1 parts per million. And then also, when you get into humans, nitrates are in fact monitored in human drinking water, because if you get over 10 parts per million, or you have 10 parts per million exposure over a long period of time as a young person, there's definitely neurological damage. So nitrates is something that is going to be, we don't have a standard yet, a federal standard. Really, we do have a standard in the drinking water, but we don't have one in national, you know, natural native waters, but we do in our drinking water standard, and that's because 10 parts per million actually causes neurological damage. Alright, so again, the major potential source or cause of this particular pollutant is going to be fertilizers and just runoff from fertilizers. Turbidity is station 5. And turbidity is where we just have a release of solids in the waterway. And basically what we look for is what we think about is, well, can sunlight get throughout that water in order to support photosynthesis and other kinds of organisms, to warm the water, to carry on those kind of, you know, life-giving, life-necessary processes. So you don't want to have too much and you don't want to have too little. And if it's completely clear, if the water is completely clear, that means that there's actually no nutrients even in the water, and that's not a good thing. So it's one of these, you want to have it just right. You met a lot of critters that have gills, and in the waterway, if you've got a lot of erosion going on, then, you know, those solids get into their gills and they suffocate. The other thing is that solids like soil and sediments, they are charged particles, and so sometimes they'll pick up pollutants and carry those with them, and those get dissolved in the water. So turbidity is another one of those things that we look at in terms of there's a just right amount. We, again, do not have a standard for this. It's something that we've been fighting for a very long time. No state has a standard. There's no national standard. And so, again, we kind of use a state average, which is just really silly. But there is a fairly normal range, anywhere from 15, which I would say is actually kind of low for a creek like Poplar, but anywhere from 15 to 173. 173 is a little bit high in my opinion, but you know, anything way above that, you've probably had a major flooding event. Anything way below that, you may not have enough nutrients to support life. So that would be kind of the range that I would look at. And then sources of turbidity are going to be erosion. Anytime that there's more water kicking into the system, that's going to cause those banks to erode. It's also going to cause the embeddedness of the rocks to lift up, and so you're going to have sediment that's taking off and floating in those riverways. Dissolved oxygen is just what it says. It's the amount of oxygen that is dissolved into your waterway. So we had 3 milligrams per liter at 16 degrees Celsius according to our Poplar Creek data. And the range of acceptability is 4 to 12. Honestly, you can't have too much dissolved oxygen. You know, it's one of those things where the higher the number, the better it is. But anything below 4, you know, between 3 and 4, your animals are going to be in stress. Anything below 2, and you've got suffocation going on. So you probably I would see couples anywhere around a 3. I would start thinking, okay, nitrates, phosphates are probably pretty high. And look at that. So potential sources of or causes of dissolved oxygen problems would be eutrophication, which would mean we've got some fertilizers, nutrients going into the waterway, which have caused a bloom, and as we said earlier, that bloom then dies and then it has to be decomposed. So that would be something that would cause the numbers to go down. And we've talked about the fact too that the way those numbers get back up again is by freezing water. So we're heading into a really important time of year for our waterways, and that is freezing. I mean, it really does need to freeze. The second part to that station is BOD, which is biological oxygen demand. And so this is kind of a different number than dissolved oxygen. Dissolved oxygen is the amount of oxygen that's actually available in the water, and BOD has to do with, well, then what percentage of that water, that oxygen is actually available and our organisms are using. So we had 0 milligrams at 16 degrees, so 0 to 6.3 milligrams, that's really a pretty normal amount. You want to see about that much available to organisms. And the same things that cause BOD to go down, it just means that, you know, it's the same thing. If there's not a lot of oxygen involved, not a lot of dissolved oxygen available to the organisms, then their BOD range is going to go down. If there is a lot that's available, then, you know, that number goes up. All right, station 7 was MBIs. And we had an MBI of 4.9. And MBI, what you want to remember is the lower the number, the better. So what's hard about this, and one of the reasons I've been had to use the sheet is, you know, some numbers, some of these pollutants you want a high number, some of them you want a low number, and so it gets to be kind of confusing. You've only had a few days to work on that, so that's why you're going to have this to help you work on. But MBI, that's your macroinvertebrate biodiversity index, and as I've said before, critters can't lie. They are the best indicator of what's really going on. They are truly the long-term picture of what's happening in your waterway, whereas the chemical abiotics is just a snapshot. You're just taking a sample, and that's what you catch is what you capture. Whereas the critters that are there, they really reflect the long-term average of that particular waterway, and so that's why I like the MBI so much. So in this case, we found an MBI of 4.9, which is actually not the one that we found right this year. We found a little bit higher one, but in our fake data that you were supposed to look at, we had a 4.9, so anything less than 6 really indicates pretty good water quality. 6.1 to 7.5 is fair. Anything above an 8 is going to be poor water quality. What causes that then? What are some things that could cause an MBI number to go up? Well, it's as simple as the type of tolerance. You know, the critters that are there, if there's a lot of pollutants and they're not tolerant to pollutant, they're either going to move or they're going to die. One of the two things are going to happen. And so those are really the good indicator that something's going on. Nitrates, phosphates, dissolved oxygen, you know, something else is happening. And that's why you need the abiotic test, because if your MBI changes, you want to know chemically what's going on, and that's why we have that there. So then you were supposed to find a couple of trends through the MBI, find a couple of things that went on by using that data, and so I hope that you found it interesting that we had so many years of data. So you were looking at you know, the data sheets. So we had data ranging from 1996 to 2006. And I think probably one of the most striking things that you probably found is that it does fluctuate. Some years it goes up, some years it goes down. It definitely fluctuates between a high 4 and a high 5 for the most part in that range. So somewhere between 4 and 6 has been our number for a pretty long time. And I think in our data we found that it was still there too. So you know, overall all over those years. If you really get into the data, you can actually see fluctuations of certain organisms, and you can see cycles of organisms. So one of the things that I've noticed and not really been able to document for sure is that, for example, stoneflies seem to be on about a 7-year cycle. Every 7 years we see a big influx of those. But you can look at those kinds of things, and I don't know if you guys noticed any more of those trends. And if you did, it'll be fun to see those, and then we can kind of talk about those and confirm those when I'm back in class. All right, so then that gets us to the stormwater, those stormwater cases and the case studies. So the first one is the Citco case study, and it's a refinery, and it says what type of operation is this plant, what does it do. So to determine that, you would have looked at the stormwater MPDS permit, and as you look at that first page, it tells you what it does, and it's an oil refinery, so it takes raw material of oil and turns it into gasoline products. Diesel, this one for example makes diesel fuel, turbine fuel, aromatic solvents, a couple different kinds of solvents, along with it doesn't make actual gasoline, but it makes probably sends that to a different refinery, the stuff that's refined for gasoline, but it makes, you know, the other kinds of other kinds of products. So then it asks a bunch of questions about hexavalent chromium, which there was another sheet in here for you to do some research. So what is hexavalent chromium used for? It's actually a pigment and a dye, and it's also used as an anti-corrosive. So it's just used in the processing plants to keep the materials, keep the metal parts of the machinery working. On the bad side, though, it is a known carcinogen, and so that's why I want you guys to kind of check it out. Its normal range is 0 to 0.1 milligrams, or 100 parts per million, is what we actually looked up. And so then you were supposed to look through here, and on about the third page in, and you can take a look at these because I've left these behind for you guys, so you can double check this for you. If you look at this, there's two different numbers. So one of them is talking about the outfall. So an outfall is an actual where the pipe comes out. So what they're looking at is how much would come out of their outfall. And there's two different. There's a load limit and then there's a concentration limit. So their load limit on a 30-day average is 0.5, which is really high. It's much higher than what is recommended to be safe. And then their daily maximum is 1.2. So then, according to the regulation, they're only allowed to release in a 30-day amount 0.1. So they are in violation of that particular amount. And then also the maximum that they can release in a day is 0.3, and they're releasing 1.2. So they're not releasing a safe amount of hexavalent chromium. So what would you do with something like this? This is kind of where we're going, because we are going to talk more about this particular case. I wanted you just to be able to kind of look at a stormwater MPDES plan to get it. So when we talk about stormwater, you've been familiar with them a little bit. But here's what we would do. We would look at this data. We would see that, and in fact we did, we being my watershed group, and then we write a letter to the EPA and say, hey, by the way, did you notice that this is a very high amount of hexavalent chromium, and it needs to be looked at. The NPDES laws we're going to talk about in a lot more detail later. You know, it's a great idea, but the truth is they don't have enough people monitoring it, and so if public does not make comments on it, a lot of times these things just go through. And I know I get a stack of them, probably about this high every month of the different plans that kind of come through, and you know, it's hard for everybody to keep track of all of them, and have to go through them in detail and make sure everything is okay, but they're not. So at any rate, this plant and their plan is definitely in violation, and needs to be addressed, and it'll be interesting to see. This is a plan from 2012. They have to submit one every year. It'd be interesting to find the other two and see if they've actually reduced those amounts, and see if they're back in compliance. My guess is they're not, but we will see. Alright, the next one is right here in Elgin. So this is Hoffer Plastics, and again, there was a plan in there for you that you had to read, and again, to figure out what they do, you just look at the first page of the MPDES and read it, and it tells you exactly what the company does. And then it will also tell you other information like what body of water does it discharge into. So to find that, you move into the next page and you look at the top, and this says the Fox River, and it gives the actual latitude and longitude. If you were interested in finding that, you could just go on a topo map and find that latitude, longitude, figure out what road you need to go on, and you could actually see it. The next question on here is a designated use. Is a part of the Clean Water Act of 1973, and you'll be learning about that. Every body of water has a list of uses, and the water quality standards are set according to that type of use. So when you look at this, I look at the rivers at the top there, and then I go down. It's got designated uses, and then next to designated uses it has the pollutants that are causing the impairment. So it's kind of this next row down. So the designated uses of the Fox River are for fish consumption. So in other words, according to Clean Water Act, we want you to be able to eat the fish. Primary contact, we want you to be able to swim in it. And aquatic life, we want it to be healthy for aquatic life. However, the Fox River, that stretch of Fox River, is impaired for those uses due to PCBs, fecal coliform, and then also alteration of the stream size, benzenes, metachlorals, flow regimen alterations, and then total phosphorus would be the other reason. So it just kind of tells you exactly why you can't use those, and that would be the other thing I wanted you to be able to read, is read these guys and be able to figure out which waterway and if they're impaired and that kind of thing. Alright, so that is Stormwater Case 2. I know I'm going through these really fast. Which gets us to 10. And 10, let me just remind you, was where you had to kind of look at these, and you had to decide where you would put the homes. And use that information to figure out where you were going to put them. So based on all the information, what you should have determined is that you would have wanted the homes to be primarily in the yellow region, so in that strip there, because the rest of that sediment is not really conducive to building homes. It's not really conducive to basements. It's not conducive to foundations. It's very limited soil. But here's the actuality. Here's what really happens. They'll build the homes where they want to build the homes. You know, so it probably the development really would have been spread throughout equally to give everybody a a certain amount of acreage, and that happens often. I mean, they can use engineering to fix soils that are not great for building on. One of the things that we just can't engineer is water, and the way water's going to go. And so if it's a limited soil because it's a hydrate kind of soil, you really want to avoid building on that, and you really want to avoid purchasing anything that's built on something like that, which gets us to the next case, which is 11. So hopefully that was good for 10. Okay, so in the yellow region, so in this paper, I'm not good at this, you would I'm really not good at this. I can't do that. You would have drawn on this end. You would have wanted your houses to be on that end. Okay. Alright. So then that gets us to 11. Both of these are actually real cases. The case 10 didn't come before us, but case 11 did, the one in Barrington, this one did come before our Soil and Water Conservation District office. So just to remind you, this is what the property looked like. And you had to use the information there to figure out about the soils. And what you guys should have figured out is that there's no way you can put a septic field in this because this has got standing water in it. So septic field is not a good idea. And you probably didn't want to have any basements in it. And definitely, a crawl space would be about it. This particular development has come before us. It's actually probably going to come up again soon. We've seen it, I don't know, 3 or 4 times now. They keep bringing this development to us for our approval. We are the Soil and Water Conservation District. We are not a regulating body. We're just a advisory body, and we would never. I don't think we'd ever approve septic fields on this property, and we would certainly never approve basements of any kind on this property. This property, there's so much water running through there, they would need 2 sump pumps at least in their basement. The first time that there's any kind of power outage or one of their pumps goes bad, they've got a basement full of water. So not a good place to build water. These are the kind of their houses. These are the kind of developments that keep me up at night when these come before us, because I just think, oh my gosh, if somebody builds them, then these people are, they're purchasing a home that's going to turn into a nightmare really fast, and that's, I don't know, I think it's criminal, in my very humble opinion. That is kind of a criminal thing. Alright, so then the other thing I showed you guys is a septic tank absorption field study. And basically, when you read these studies, the lower the number, that means that it's not really limited. The higher the number means that it's really limited. And so when we do these, we get these reports, and they're color coded. And orange means it's very limited. And so we just open up the page, and It's all red. So the entire property where they want to build, you know, these homes, it's completely inundated with water. And depending on where that water is, where that water table is, if you think about when we were learning about the water cycle, tells you how deep. And this water table was found to be about 5 feet below the surface, and they want to put in 8-foot basements. So it doesn't really make a lot of sense. It's not really a good idea, but it happens. You know, they still build them, and despite warnings. And so one of the things I have to make sure I show you guys is how to read a soil map, so that none of you, you know, purchase a home that was built someplace where, you know, it's just going to turn into a nightmare for you. So that is for sure. Okay, so that was 1 through 11. It was really fast. Let's take a deep breath. According to my clock here, we probably have about 10 more minutes or so to get through the rest of it. Okay. So that gets us to the Q value, which probably was a little bit of a struggle for you guys, which is good, because that means your brains had to stretch and grow. Alright, so here is my advice to you. If you didn't figure out this Q value yet, or you just copied from somebody, you are in trouble, and this is not going to work for you. So I want you to go back and do it again, and do it for real, because otherwise you're going to be lost when you have to do this tomorrow on the test. Okay, so the best things to help you are the Q value sheets that are samples that have it done for you. Okay, those are excellent. The other thing you need to be able to do the Q value is you need all of the data sheets. Okay, so everything that shows you the Q values. Now, why do we do a Q value? Well, we do a Q value because it's kind of a standardization so that we can compare water quality across the country. We can take into account how these different chemicals react to different temperatures, for example. It's not as synergistic. It doesn't take into account synergy at all, which, you know, we've been talking about the fact that that needs to happen, but we just don't have anything like that. But this is a standardizing kind of situation, and that's why we want to be able to do it. Okay, so if you've got your Q value sitting in front of you, and if you don't have a Q value sitting in front of you, maybe go get a blank one so you can at least look at it, but don't cheat and fill it in, because you really have to struggle and do this to learn it. Okay. So our water, according to our water, I used all of the information that was just on the lab sheet that I gave you guys, and we just kind of inserted everything here into your Q value fake data. Okay. So water temperature was 16 degrees. And that was the water temperature at the site, and then 1 mile upstream, so we came up with a temperature change of 0. So you would have an average, so if you go over to the average columns, it would be 16, and if you go over to the to where the temperature difference, you actually do a subtraction, you come up with 0. Alright, so that means that you then have to go to, there's a couple of different charts that you have to use. And so the first one is the temperature one. Sorry, I should have these in order. I should have them in order of how they were put in the book. So you want to use this first one. And you find the 0 temperature change. And you know it's the right one because it says change in temperature at the top. Okay? You find the 0, and then the Q value that it matches to is 93, which is actually the maximum value. So on this data chart then, you put a 93. Yeah, I can't do this. Are you guys laughing at me yet? Because I'm feeling seasick. I'm pretty sure you are too. So there's the 93 there, and then you multiply by the 0.11 to get 10.23. Alright. Next comes dissolved oxygen, which is 3. And so then you use the dissolved oxygen chart, which is this one. Oops, sorry. Oh, no, I'm lying to you. First you have to use this crazy thing. Alright, so hopefully you guys figured that out. So, you take the 3, you find the 3. I don't know how I'm going to be able to do this. Alright, I'm not going to be able to do this. I'll have to make sure you guys have these. Okay, so, here's my 3 over here. I'm going to line that up to the temperature which is at the top, the 16. So you literally have to take a paper and line it up from the 3 on the bottom to the top here, which is at 16. I line it up. Okay? Once you have it lined up, okay, it hits this 30 mark. Alright, it will hit this 30 mark. There we go. Somebody who figured this out, could you help somebody who couldn't figure it out since I'm not there? I'm sure somebody figured it out. You guys are all so smart. Then you put that one into this Q value, the dissolved oxygen Q value chart. That looks like this. And you find the 30. And that came out to be a Q of a 20. Multiply that by the weighting value of 0.18 and you end up with a 3.6. Alright, then you transfer your data, the 3's, and then you subtract them from the dissolved oxygen, because you would wait 5 days to actually do the test again. You keep measuring it. So we come up with a 0.5, sorry, and then the weighting factor is 94. Sorry, the Q value is 94, the weighting value is 0.2, we come up with 11.28. Alright. pH was 8, so then we come up with a Q value of 82, 0.12 is the weighting value, a 9.8. Now, next we've got the orthophosphate, which we don't qualify that, we don't quantify that, so it just stays the 0.17 and it's not put then into the interpretation of the overall value. We look at our total phosphates. If it was a 0, it would be an average of 0, 99, multiplied by that 0.11 is 10.89. Now, I do want to tell you guys, because I can't remember exactly which test it is, but often the Q values, what you get is going to land between a couple of values. Okay, so let's say, for example, you ended up with like an 84, but it's only in rounded numbers. Then just take, you know, what you think to be the in-between, the best matchup possible. So it is a little bit subjective. So actually all of your overall Q values are going to be overall ranges. So, in other words, what I give you guys could be plus or minus 2 or 3 points, either way, depending on how you interpreted some of these that fall in between. Okay, so, and that's perfectly okay, that happens. Alright, now, with the data that we've got here, there's no nitrate data. Okay, because there's no nitrate data, then you don't put anything in, don't put any zeros in or anything, because that would actually translate to a Q value. But then you also don't use the 0.10 weighting factor. Alright, so we'll get to that in a second. The next one down is transparency or turbidity. Okay, and this is a two-step process. So, to determine turbidity, you first must transfer it from centimeters into NTUs. NTUs. Okay, so the first column here where my finger is, that's your transparency. So it was 13 centimeters. Somebody was nice enough to circle it there. 13 between 14. Then that translates into an NTU, and then the NTU gets transferred into a Q value. Okay, so 2 steps there. And you would also make sure that you record those 2 steps here. Okay. Now, I just gave you the data for the fecal coliforms, and so that 37 is the actual Q value, because the coliforms, they're tough to do. I don't do them anymore because I worry about them, you know, having E. coli in a refrigerator and then in my incubators. It just makes me a little nervous, so we don't do that one anymore. We just pretend like we do it. Alright, so then we got 37 for our Q value and a weighted value of 0.17. Okay, so now, here's what you do. Hopefully I can do this without making anyone nauseous. Alright, you're going to add up all of the weight factors. If you used all the weight factors, the weight factor would be a 1. but since we did not have nitrates, the weight factor is 0.9. Then I added up all of the Q values that were multiplied by a weighting factor, so your third column, and came up with a 54.11. Now keep in mind, you could be plus or minus on either side, 3 points or so, depending on how you interpreted some of them. Okay, and that's perfectly okay. Then you divide the total value that you came up by the weighting factor, and I came up with a 60%. And now I have to interpret it. I go over to this part over here. I've got to really figure out this opposite thing, and it tells me that I have medium, medium water quality, which, what does that mean? Medium water quality. Oh darn. It means nothing unless you have a bunch of years of data. Then you could say, well, it's staying the same, or it's getting more, it's that percentage is dropping. It's getting lower and lower and lower, and then the water quality is getting lower, or it's getting up, higher. It's probably most likely going to be like the MBIs, where it's just kind of, woo, floating up and down between a range, a high and a low, and that would be fairly normal. But by using the Q value, we can really standardize data, abiotic data, so that it can be used, we can compare it anywhere in the world. And that's the whole point of using those Q values. And I'm pretty sure you probably use Q values for sure in AP chemistry. You talked about Q values and the need for them. And I'm not sure if in regular chemistry you would have, but I know in AP you would have talked about that. But that's the whole point, and here's the practical application for that. Alright, there's two last things that you had to do, and I can't believe that I have talked for 40 minutes already, you poor dears. What does the data mean? That was the sheet at station 13. It looks like this. Okay, and I gave you some fake data and that you were supposed to interpret it. So here's what I want you to get out of that. Two locations, location A, location B. Dissolved oxygen at location A is 10 parts per million. Location B, it's a 3. Obviously, the dissolved oxygen at location A is better than location B. Location B, those critters are going to be in stress. If I go to temperature, I've got 18 degrees and I've got 27 degrees at location B. That might, in fact, support the 3. If you've got a higher temperature, maybe that's a good temperature that's just causing that that water to release its oxygen, whereas location A maybe is holding. Maybe there's a canopy cover there or something. All right, pH 7.5 and a 6. Both of those are in the normal range. With a 6 being at that lower end, you might want to check out location B. Maybe there's something that's releasing some kind of, hydrogen ions into that region. That might be something. Nitrates, we have 2 parts per million at location A, and we have 6 at location B. So actually, both of these are not in great condition. Both of them kind of have high nitrates levels. Phosphates, we've got both of them within normal range, so those are okay. I do want to take a second because we have not done our ecology unit, so I want to talk about, sorry, can you hear that? I was worried about weird noises from my household coming up when I was doing this. Here come the dogs. So diversity is the number of different species. That's your taxa. And so we want to see a high taxa number. We want to see a high diversity. Abundance is the number, sheer number of organisms you found. Why is diversity better than abundance? I'm going to give you 10 seconds to think about that. Why is diversity more important than abundance in a sample? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yell it out. If you yelled out that diversity is it's the measure of having more critters. I mean, it tells us that there's actually more critters that are able to be supported by that region. Then you're right. We could pull out 525 bloodworms, which have a tolerance value of 11. That's not good. We don't want that. And so abundance, although abundance is important, we really, for our samples, only need between 50 and 100 organisms. So it doesn't even help us to find 525 of them. But the fact that we came up with 16 different organisms at location A, different species, and only 7 at B, kind of tells us a little bit about that. Question 2 wants us to talk about the biotic factors, which represent the biotic factors. That's the diversity and the abundance. And then location A was healthier than location B, is what I would have come up with. And then some hypothesis for that. What could have caused if these were the same in the same stream, why is it that location B is not as healthy as location A? And there could be a maybe location B doesn't have trees on it, so it has no canopy cover. Maybe there's some kind of industry, or maybe there's a bridge going over, or maybe there's a stormwater discharge going through there, and so that it's contributing a high amount of nitrates or a higher amount of phosphates, and that's impacting the overall water quality. So anything like that would be appropriate. All right. Final reminder about things you need to know. You're going to be able to calculate an MBI. You have to be able to do a Q value, and you're also going to have to make a sketch, okay, from an aerial photo. Those are the 3 things that you'll be responsible for. You will not have anything to help you on the first day, but on the second day you will be able to have your lab from this discussion that we're having today. So email me if you guys have any other questions or any other concerns. And I think that's it. I'm looking forward to it. Usually everybody does pretty well on this test because it's so hands-on and everything. So, all right. Make sure you clean up everything. Be nice to the sub. I hope you're very nice. All right. Bye.